Hello, I'm Adam, the first author of this paper, pursuing overall welfare in federated learning through sequential decision making. In practice, not all clients can be equally benefited from a global model in federated learning. This is related to the notion of client-level fairness. It's about the uniformity of the performance distribution of the global model across clients. As you can see here, local losses of the second and the third clients are higher than the others. This is surely an unfair situation. It is caused by the statistical heterogeneity inherent in the federated system. Notably, this can be simply addressed by using an adaptive mixing coefficient. The rationale is simple, imposing larger coefficients to the clients with larger losses. The adaptive mixing coefficient is determined by the server round by round. However, the server can only use a single response vector for updating the single mixing coefficients. This is a sample division situation for the server, and it is not explicitly considered before. So, this work starts from this question. How can you improve the scheme of deciding mixing coefficients so that it is truly adaptive, even under the sample division condition? We start from the discovery that existing fair FPL algorithms can be unified into an online convex optimization framework. Interestingly, this OCO framework is one of the best strategies to make decisions under the sample division situation. The hidden OCO algorithm that can bind the existing works together is an exponentiated gradient. It has a closed form update formula as follows. So, when we plug components summarized in this table to the closed form update formula, we can retrieve all the mixing coefficients of fair FPL algorithms. However, existing methods were not originally invented as online algorithms, so we can easily find suboptimal designs in terms of sequential decision making. We can adopt better OCO objective, named as follow the regularized leader, or FTLL. First, it adopts stateful decision-making mechanism, counting for all previous decision losses, and second, it also adopts a time-varying step size or time-varying regularizer. For the better choice of a decision loss, we can listen to the wisdom of online portfolio selection framework. Since this framework bears resemblance to our situation, we can adopt the negative logarithmic growth in this framework as our decision loss. Sometimes we cannot observe all entries of a response vector due to the client sampling scheme in the cross-device federated learning setting. By adopting the doubly robust estimator, we can address this situation since it is an unbiased estimator of unknown fully observed response vector. Based on previous ingredients, we can now make a better decision. Before going on, let's see two practical federated learning settings. First, the cross-silo setting, where the number of clients k is smaller than the total allowance t. Second, the cross-divide setting, where the inequality is flipped. We should focus on the fact that the dependency on k and t is different in each setting, and this should be considered in practice. Here is the algorithm for the cross-silo setting. We can directly adopt Euler-Newton step algorithm since we usually observe all local losses in cross-silo setting. For the cross-divide setting, we can resort to the following objective with the negative entropy regularizer, which is also a direct instantiation of FTLL objective. Here is the theorem for the regret upper bound of proposed method for the cross-silo setting, which is logarithmic in t, and the regret upper bound for the cross-divide setting, which is square root of t, but the dependency on k is much smaller, which is essential for the cross-divide setting, where there are massive number of clients. Even if the client sampling is required, the proposed method can achieve the same sublinear regret in expectation. To evaluate our method, we conduct experiments on 6 datasets, 3 for cross-silo and 3 for cross-divide settings. Empirically, proposed algorithm AAggFF consistently shows better performances comparing to baselines in both FL settings. Especially, the worst case performance is improved while maintaining the average performance. Moreover, the Gini coefficient of the performance distribution is small, which is directly translated into the guarantee of the client-level fairness. In this work, we propose AAggFF, which aims to find better mixing coefficients for making uniform performance distribution. It is based on the discovery that existing fair FL method can be unified into OCO framework, and adopting the OCO is crucial for the sample diffusion situation when deciding an adaptive mixing coefficient. We further specialize our method into two practical settings, and we show that our method can guarantee vanishing regrets. Lastly, we present that our method can achieve better client-level fairness than existing algorithms. This is the end of the presentation. Thank you.